Alright, we're going to talk about circle basics, and then we'll also talk about tangents. So let's just start with labeling different parts of the circle. This part right here is called the center of the circle, and we name circles using the center of the circle. The distance all the way across the circle going through the center point, that is called the diameter. Halfway across the circle, so from the center point to a point on the circle, that is called the radius. And then we have points both on the interior of the circle and on the exterior of the circle. There's points on the actual circle itself. This point right here is an interior point. And this point right here is an example of an exterior point. Alright, down here, this is called a chord. And we're going to write some definitions here. It's not a lot of space, but we'll try to fit everything in. A chord is a segment, and I'm going to underline segment because that's an important word. Segment that connects, a segment that connects 2 points on a circle. So if you just find any 2 points on a circle and you connect the 2 points with a line segment, that would create a chord. This right here is called a secant, and it's very similar to a chord. Really the only difference is that it is a line instead of a line segment. So actually, anytime you have a secant, you could take just a piece of that secant, and that would be a chord. So the only difference is the secant keeps going, it doesn't have the endpoints. So if I were to take this chord and extend it to infinity in this direction and extend it to infinity in that direction, that would make that a secant as well. So a secant is a line. So over here I underline segment for chord. For a secant, I'm underlining a line that intersects a circle at 2 points. And I'm going to underline 2. It intersects it at 2 points. And the reason for that is the next thing we're going to talk about right here, this is called a tangent. And because of the limited amount of space on this side, I'm actually going to write the definition for tangent over here on the other side. But a tangent intersects a circle at 1 point. So a secant intersects the circle at 2 points. Tangent intersects the circle at 1 point. So only 1 point. And that 1 point where the tangent does intersect the circle, that point is called the point of tangency. So the point of tangency is the point where the tangent intersects the circle. And kind of run out of room there, it's looking a little sloppy. But you have a tangent and intersects the circle at 1 point. That point where the tangent intersects the circle, that is called the point of tangency. So those are the different things related to a circle that we're going to talk about today. So let's look down here at example 1. It says L is the center of this circle. Round answers to the nearest tenth if necessary. So first thing we're going to do is name the circle. We name a circle based off of its center. And when we write the name of a circle, we use the circle symbol and then that center point. So since the center point is L, we call it circle L. This is circle L. Alright, Next thing we want to do is name all radii, and that's just the plural form for radius. So you have more than one radius, then you have radii. Remember, a radius goes from the center point to any point on the circle. So I see 3 of them right here that have already been drawn for us. Line segment LN, line segment LR, and line segment LM. All 3 of those have been drawn. Line segment LN, LR, and LM. Each one of those is a radius. Now, there are some other radii that are not shown, but could exist. And so because the directions did not specify that we only wanted to name all the radii shown, we need to go ahead and include these as well. And I'm going to put these in parentheses because they're not shown. But there's another, we could draw a line segment from L to Q to create a radius. So there is a radii from L to Q. And we could also do it from L to T. Basically from that center point to any point on the circle. So however many points you have named on the circle, that's how many radii you can have. So the ones inside the parentheses are not shown, but they are radii that would need to be named based on those directions. Alright, name the diameter. Well, the diameter goes from one end of the circle all the way to the other end, going through the center point. So line segment MN is a diameter. Now, some people may be thinking they're trying to apply the same thought with a radius, like maybe there's one that's not drawn yet. The tricky thing about that is for it to be a diameter, it has to go through the center point. So, for example, from Q to T, that straight line, it comes close, but I don't think it's going to go through that center point, and we have to know that it's going to go through the center point, not even just, hey, it looks like it probably would. So with a diameter, it usually typically has to be drawn, unless there's some other information that helps you know that it would go through the center point. Alright, what is the length of any radius in this circle? Well, they've labeled the radius as 16 meters. So this would be 16 meters, this would be 16 meters. The distance from L to Q would be 16 meters. A radius is the same distance no matter where it's drawn. What would be the length of any diameter of the circle? Diameter is always twice as long as the radius. So 16 plus 16, or 16 times 2, would be 32 meters. Okay, what is the circumference of circle L? Well, circumference is either 2 pi r or pi times diameter. So really all we need to do, since we have the diameter, is multiply it by pi. You're doing pi times diameter. And it told us in the directions to round to the nearest tenth if necessary. So if we do 32 times pi, that would round to 100.5 meters. So that's the distance around the outside of the circle. That's the circumference. Okay, area is pi r squared. So the radius is 16. So pi times 16 squared. And 16 squared is 256. So for pi r squared, for the area, we get 256 pi. And if we're rounding that to the nearest tenth, that would be approximately 804.2 meters squared. Area is always units squared. Alright, next one. Name all the interior points shown. Well, we have a lot of points on the circle, but the center point is actually the only point on the interior. So the only one shown is point L. Name all the exterior points shown. Okay, well the only points on the exterior would be P and S. Point P and point S. Alright, let's name all the chords. Now this one's a little tricky. Remember, a chord is a segment that connects 2 points on a circle. So basically, if you're not worried about what's been shown and what hasn't been shown, you could pick any 2 points on a circle and they would create a chord. Now let's start with the ones that are already shown. I see a chord from line segment from M to T, line segment MT. And I see the diameter is always a chord because the endpoints of diameters are 2 points on the circle. So line segment MN is also a chord. The diameter is the longest possible chord in a circle. Alright, now those are the only chords that have been shown, but remember I can create a chord with any 2 points on a circle. So I could go from M to T, M to R, M to N, M to Q. Any of those would work. So let's put them in parentheses, the ones that are chords in the circle that are not shown yet. They haven't actually been drawn. So we already got MT and MN, but we don't have MR or MQ. So line segment MR and line segment MQ. Okay, now that was everything coming from M. So let's go to another point. Let's do T. I could have line segment TR, TN, TQ, all of those are possible chords on this circle. From R, we've already gone to M and T, but R could go to N and Q also. So line segment RN and RQ. And then I could also have one from N to Q. Yep. Okay, so there's all the chords in this circle. The ones in parentheses are the ones that are not shown. They haven't actually drawn the segment yet, but it does exist. Anytime you got 2 points, a line or a segment does exist between those, even if it hasn't been drawn yet. Alright, name all the secants. Now remember, the only difference between a chord and a secant, the only difference between a chord and a secant is that a secant is a line where a chord is a line segment. So basically all those things that we just wrote down as chords, you change it from a segment to a line and you got a secant. Now let's look at what's actually been shown, what's actually been drawn in the picture already for us. How many secants have actually been drawn? Well, I only see 2 lines, and this one only intersects the circle at 1 point. So that's not a secant. This line intersects the circle at 2 points. So line MT is a secant. It's the only one that's been drawn on the picture. But there's a whole bunch that haven't been drawn yet. I could draw a line from M to N, or through M and N. I could just take this diameter and extend it to infinity in both directions. And basically, I'm just taking all of these chords and changing the segment to a line. I could have a line going through points M and R, through points M and Q, T and R, T and N, and so forth. Only difference between a chord and a secant is that a chord is a segment and a secant is a line. Alright, let's name a tangent. Name a tangent. Okay, remember this line right here only intersects the circle at 1 point, and so that makes that a tangent. Now when you name a line, you just need 2 points. I got 3 points here, so I can pick any 2 of them and put it in any order I want. So I could call it line PQ, PS, QS, SP, whatever I want to call it. Just need 2 of those points. I'm just going to choose to call it line PS. And that was the only tangent here. The only tangent that was shown in the picture. And a tangent thing, a tangent C is kind of a tricky thing. You probably could draw a tangent with S and N, but I can't be 100% sure about that, if N is too far around or not. So we're just not going to worry about drawing any that are not shown. It's kind of like the diameter thing earlier. It's hard to know if that diameter would go straight through the center or not. It's kind of hard to know if this would perfectly intersect the circle at only 1 point or if it would intersect it more than once. So we're just going to leave the tangent as line PS. And then we want to name the point of tangent C. Remember, that's where the tangent intersects the circle at. And here's line PS, and it intersects the circle at point Q. So point Q is the point of tangent C. All right, let's turn the page. All right, we have a theorem, and it says if a line is a tangent to a circle, then it is perpendicular to the radius drawn to the point of tangent C. So right here in this example, it says refer to circle C with tangent line segment AB. So it tells us that this is tangent to the circle. So it's intersecting the circle at one point, and point B is that point, so it's the point of tangency. That tangent is going to be perpendicular to the radius that's drawn to that point of tangency. So here's the radius, and it's drawn to point B. So they are going to be perpendicular to each other. Anytime you have that radius and a tangent intersecting at that point of tangency, they are going to be perpendicular. They're going to form a right angle. So in this situation, we have a right triangle based on this theorem. Well, I know that's a right angle, so we have a right triangle. We want to find out what x is. Well, on this right triangle, I know what two of the sides are, 5 and 12. So I can set up Pythagorean theorem to find out what that third side is. And remember, C is the hypotenuse. That's the side opposite the right angle, so that's this side, which we do not know. So these sides are A and B. So 5 and 12 can go in for A and B. 5 squared is 25. 12 squared is 144. I add those together, I get 169. I want to get rid of this squared, so we're going to do the square root. And that will tell me that side C has a length of 13. So I know the length of this entire side is 13. But all I want is x, which is just part of that side. Well, remember, a radius is the same no matter where on the circle you draw it. It should go from the center point to a point on the circle, but that has to be the same everywhere. So if it's 5 here, it's 5 here. So this side length of 13 is being split into two parts. This part's 5. I can find out what x is by simply subtracting 5 from 13. And I find out that x has to be 8. Okay, let's look at another theorem. It says if two segments from the same exterior point are tangent to a circle, then they are congruent. So here's point P, which is the exterior point, and we have two tangent segments drawn from that same exterior point. Based on this theorem, anytime we have that situation, these segments have to be congruent to each other. So congruent means they have equal measures, so I'm going to set these measures equal to each other, and we can solve for x. So I'm trying to get x by itself. 3 is being subtracted, so I'm going to do the opposite and add it. And then x is being multiplied by 2, so we divide by 2. And find out that x is 15. All right. When circles are inscribed in polygons, the polygons are said to be circumscribed polygons. In such polygons, each side is tangent to the circle. So here's an example of a circle that has been inscribed. It's inside that polygon where it is intersecting each side of the polygon at one point. The polygon is circumscribed. It's coming around the circle, and each side of the polygon is a tangent to that circle. Well, what we just learned was that when you have two tangents coming from the same exterior point, they're going to be congruent to each other. So from point T here, you have two tangent segments, so those have to be congruent. From point W, you have two tangent segments, so those have to be congruent. And then from point R, you have two tangent segments, so those also have to be congruent. So with that in mind, if the perimeter of triangle TRW is 50, the distance from T to K is 3, and the distance from W to M is 9.5, we want to find the distance from T to R. That's what we want to find right there. Well, let's do the work. We know that these are congruent, so if this is 3, the distance from T to L is 3. I know that the distance from W to M is 9.5, so the distance from W to K also has to be 9.5. And while I wasn't given one of these, I was told that the perimeter is 50. So I know that all these sides should add up to 50. Well, let's see what I got so far. I got 3, 3, 9.5, and 9.5. So if I add all those up, I'm going to get 25. So what I have adds up to 25. Well, the whole thing should be 50. So what's left? Still got 25 left. And there's only two parts here that have to add up to 25, and they're marked congruent. So if I have two congruent parts that add up to 25, then each of those is going to be half of 25, which is 12.5. So I know this is 12.5, and I know this is 12.5. So now, what is the distance from T to R? I just got to add 12.5 plus 3. And we get 15.5. Alright, let's look down here at example 5. This is our last one. Alright, given that the distance from O to A is 12 and the distance from O to B is 6, and the measure of angle BAC, this entire thing over here, is 60 degrees, find the following. Round to nearest tenth if necessary. Okay, now I did not label these in the picture yet because they're a little tricky because they're split up into different parts. So I'm going to wait and see if I can figure out how to split those up in just a minute. Alright, the distance from O to C. Well, O to C, that's a radius, and it's got to be the same as every other radii in that circle. So since this is 6, I know the distance from O to C is 6. The distance from E to D, that is a diameter, so it's going to be twice as long as the radius, because this part would be 6 and this part would be 6. They got to add up to 12. The distance from A to B. Now, these, both of them are tangents to the circle from the same point, so I know that they're congruent. Also know that they are tangent to the circle, so when you see a radius drawn to that same point of tangency, I know that those are perpendicular. I know they're forming right angles. In both of these cases, we have that same situation happening. So, here is a right triangle. I was told the distance from O to A is 12, and I know the distance from O to B is 6, so I have 2 of the 3 sides of that right triangle, so I can do Pythagorean theorem to find the one missing side. So the hypotenuse is 12, so I can put 6 in for A or B, does not matter which one. 6 squared is 36, 12 squared is 144. I'm trying to solve for A, so I'm going to subtract the 36 to get rid of that. And then I want to get rid of that squared, so I do the opposite operation and take the square root. And it said to round to nearest tenth, so we'll get approximately 10.4. And remember, I was dealing with this right triangle here, and I found that third side, which is the distance from A to B. Found out that that's 10.4. And remember, I got the same scenario happening over here, a right triangle with side lengths of 12 and 6. I know that this would be 10.4 also. And remember, they're congruent because they're both tangents coming from the same exterior point. So both of those are 10.4. Then we want to find the measure of angle BAO. Okay, well, I got a couple different ways I can go about doing this, but we have angle BAC right here. And point O is equidistant from both sides of that angle. When that happens, I know that that has to be on the angle bisector. So that means because these are the same distance, this is the angle bisector of angle BAC. So since angle BAC is 60 degrees, it's being bisected. Each one of these angles is going to be half of that 60, so 30 degrees and 30 degrees. So angle BAO, the measure of angle BAO is 30 degrees. The measure of angle OCA is 90 degrees, because earlier we showed that those were perpendicular to each other. Measure of angle AOC. Now, angle AOC, I don't know that angle yet, but I know that this is 90, and I know that this is 30, and I know in any triangle the three angles have to add up to 180. So if I got 90 and 30, that's 120 degrees. So that third angle has to be 60 degrees. That's what's left. So I know that this is 60 degrees. And I have the same scenario happening in this triangle, 90 and 30, so this one has to be 60 so that they add up to 180. So angle EOC, now angle AOC and angle EOC are actually the exact same angle, just with a different name. So don't let that fool you, same angle. And then what's the distance from E to A? Well, remember the distance from O to A was 12, and the radius here is 6. So this other part has to be 6 as well. 6 plus 6 would equal 12. So the distance from E to A is 6.